Okay, so there is a really, there is a way to kind of see these phase changes using a graph. And there's two different graphs that we're going to use. The first one that we're going to look at are called heating curves. So obviously the system is getting heated up in a heating curve. That's what a heating curve shows. It's just a graph, but they call it a heating curve instead of a heating graph for some reason. And this is going to show the relationship between the molecular kinetic energy and the potential energy within a substance. Right? So we know that kinetic energy is motion. Right? Last year we had an entire unit on potential energy, where it's energy that has the, like it's energy of position or it's stored up energy, right? Like gravitational potential. When something has more height or mass, it has more potential to fall and cause, you know, a reaction or a change. Stored up energy, like in our food, in batteries, right? That's all potential. So at certain times, these states of matter have the potential to change into another phase. And so that's what we're gonna kind of look at with potential energy this year. And so we know that by adding or taking away thermal energy, that's how we can make these states go from one to another. And so since these are heating curves, we're gonna be adding thermal energy. We're gonna be putting heat in to the system. And remember, thermal energy is just heat. So as we add heat, the temperature increases and so does kinetic energy. Totally makes sense, nothing to memorize, right? As you add heat, things usually warm up, right? It increases the temperature. And we know there's that direct relationship between kinetic energy and temperature. They're besties. As one goes up, the other goes up. They do the exact same thing. If temperature goes down, then that means the kinetic goes down. So if the temperature is not changing, but thermal energy is being added, this is when we say potential energy is changing or building up. So it's kind of like you're pumping heat in, but nothing is really happening, nothing's changing, so that heat's just kind of building, and then all of a sudden it's gonna do something. So it's during that phase when, or that time when you're adding thermal energy, but the temperature is staying constant, right? And that you're like, well, how can that be? Like, why wouldn't the temperature be changing continually? And it's because some of that thermal energy is going into building up the potential to allow those molecules to start spreading apart and to start to move. And this is what it looks like. So typically you'll see that heat being added down here on the y-axis, your dependent variable. It's looking at the temperature of the water in degrees Celsius. And so this is minus 40 working its way up to 0, right? Then it kind of flatlines, has a plateau, right here. And then it goes on the increase again. And then the temperature plateaus again, and then it goes up again. All right, so there's two places where you see that it is plateauing or kind of flatlining, right? When you see it going up, then obviously that's when the temperature is on the rise, going from negative 40 to 0, 0 to 100, and then over 100. Look up here. These visually show really good what's going on. So I see that I have all my molecules tightly packed. They're as a solid, right? Not much space between them. Now I see a little bit of that solid, but then I also see some of the attraction kind of weakening, and now I see some space between some of the molecules. Okay. Now I have all the molecules have spaces between them. I don't see any chunks where it's like representing those molecules packed tight like a solid. And then as I move to this plateau, I see a lot of the liquid where there's some space, but now I see a few molecules that are kind of escaping up into the gas version or turning into that steam or water vapor. As I keep adding more and more thermal energy throughout this whole period, all of a sudden, now everything has turned into a gas. All right, so looking at this picture, you can see a ton. I could ask you probably 20 questions based on just this graph, right? I could ask you, where do you see just solid? Well, I only see solid right here. Where do I see just liquid? Well, that would be just right here. I see liquid here and I see liquid here, but it's some gas and some solid. So the place where it's only gas is right here. Only liquid. And then if I want to look for where it's only gas, it would only be this location. There is some gas here, but it's also still with some liquid, right? I could also ask, where do you see two phases at one time? Well, I see two here, and I also see two here. Those kind of match our plateau or our kind of flatline areas on the graph. And that's going to be pretty constant. Like most graphs are going to just follow these same patterns and trends. Okay, and so again, solid, liquid, where there's a little bit less attraction between the molecules, and now to the gas where they have a lot of space between them and not very much attraction at all. If you go straight from the gas to the solid, right, you have this sublimating process. If you go from the gas to the liquid, you're having condensation, liquid to the gas, evaporation or boiling. Right, so this is just kind of showing those different phase changes. All right, so here's kind of what's going on, like the explanation. So with kinetic energy, which is the energy of motion, molecules are moving around, our particles, atoms, whatever you want to call them. And it's directly related to temperature. So as kinetic, this arrow up means up. Kinetic energy increases as the temperature increases. Notice, they are doing the same thing. They are besties. Whatever one does, the other is going to do the same. Potential energy is the energy of the arrangement of the molecules, the space between them. So this is something that I've been harping on like the whole unit. This all kind of comes down to the space between the molecules. And that is actually related to potential energy. So there's something called the law of conservation of energy, where energy cannot be created or destroyed. It just kind of goes back and forth between these two main forms of energy, all right? And so if kinetic is going up, then that means potential is a constant. If potential is changing, then your kinetic energy is kind of staying constant. So they both can't do the same thing at the same time, because that'd be like you're adding energy, and that's not possible. So energy can transfer into different forms, but you can't add any energy and you can't take any energy out of the total system. So it's kind of just like this flux between the two. You go back and forth. And so temperature, the way that you know that a phase or a potential energy is changing is the temperature does not change. And this is taking place during a phase change. So when you have that solid cube of ice and it is starting to melt, the temperature is staying constant even though you're cranking up the heat. Heat is being added, and that's what's doing the melting, because that's what's actually changing the spacing between the molecules. Not changing the molecules themselves, but just the space between them. Right, so anytime you're trying to identify if potential energy is changing, just look at the temperature. When it flatlines and the temperature is like that plateau or straight, horizontal, then like here and here, then we know that that's where phase changes are taking place, and we know that that's where potential energy is taking place. So you have a weird vocab word. I think it's like the 3 Ps. Does that sound familiar? So this is what the talk is with the 3 Ps. You have the plateau area. You recognize that, right? Plateau is like this flat line, right? That's the first P, plateau. The second P is that's where a phase change is taking place. So at these plateaus, that's where phase changes are happening. So you have some solid and some liquid. Here you have some liquid and some gas. The third P is that's where potential energy is changing. All right, so the 3 Ps go together: plateau, phase change, and potential energy. At those 2 locations on the graph, phase changes are happening, potential energy is changing, and that plateau is what helped you visually kind of recognize that. So that's why I kind of put that, to help kind of put those things together. So here it says time. Sometimes it'll say time, sometimes it will say heat. So as time goes by, heat is being added to the system, because we know that because this is a heating curve. So it doesn't say heat's being added, but that's what we're understanding. So either it says time or it says heat, but it's still meaning the same thing. Like energy, heat, thermal energy is being added to this system, right? We still have temperature here. And again, it makes sense. At 0 degrees Celsius, we know that that is kind of the freezing and the melting point. So if we're adding heat to something, we're trying to melt it. And so this is where it starts to melt, right? This whole time, for this, it looks like it's maybe about, I don't know, 60 minutes. It is taking heat in, but it is not changing the temperature, right? It's stuck at 0, 0, 0 for that whole 60 minutes. And that whole 60 minutes, what's happening is the spacing between those solid water molecules is starting to increase until eventually the temperature starts to go up. And as soon as the temperature starts to rise, that's when you know that all of the solid ice is gone and it is all turned into a liquid. So it's liquid, 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 liquid until you get to 100 degrees Celsius. At that point, for all of these hundreds of minutes, 1, 2, 3, probably almost 400 minutes, it is liquid and gas, because I know a phase change is happening, so liquid going to gas, and I also know that the potential energy is changing. Potential energy is how much space is between the molecules, and so that means more and more and more space is being put between the molecules until eventually everything has turned to the gas form and it starts to rise again. Okay, so we have our solid. Notice it's showing kinetic energy is going up because temperature is going up. This is melting. This is where potential energy is going up. We're back to kinetic going up because temperature is going up. So if you're trying to identify what kinetic energy is doing, just look at the temperature. So if the temperature is constant, what do you think that means for the kinetic energy? It's also constant, right? Because again, they're besties. They're doing whatever the other one's doing. So if temperature's constant, kinetic's constant. And so that means since energy, heat is being put into the system, that energy has to transfer into something. And at that phase change, energy is being transferred into potential energy to help separate those molecules and give more space between them, right? This is where it's boiling. This is another phase change. It's a big plateau. Notice the flat lines are where our potential energy is increasing. What's happening with our temperature here? Ethan, what do you think? What's going on with our temperature?
It's phase changing.
It is, but what's our temperature through that whole time?
Staying constant.
Yeah, it's staying at 100 degrees Celsius the entire time, right? So even though like you're cranking up the heat, the temperature's stuck at 100, right? It doesn't start to go over 100 until all of the liquid has changed into a gas, because that thermal energy that you're putting in, that heat that you're putting into the liquid is changing the potential energy and the spaces between the molecules. And then finally, it starts to go up again in temperature, which means our kinetic goes up. So really, if you just get the connection that kinetic is going to do what temperature does, if it goes up or if it's constant, kinetic is going to follow that. And then where it plateaus, think of the 3 Ps: plateau, phase change happening, and potential energy is changing. Okay. All right, so heating curves are going to show the constant rate of heating over time, and this is an endothermic process because it's taking heat into the system, which obviously, again, not something to memorize. It just kind of makes sense, because if you are heating something up, it's taking heat in. Okay. All right, so this graph has these little line segments kind of marked: AB, BC, CD, D to E, and then E to F. So it shows that this is all solid, this is all liquid, and this is all gas. Here is a phase change, right? So the phase changes, in a way, you can kind of think of them like the bridge. they bridge the gap between the solid and the liquid. It's not gonna happen instantly, right? So you have this period of time. In this case, it's taking about 3 minutes to go from, and this must not be water because this is happening, this melting is happening at like 50 degrees Celsius. So I know it's not water, but it's still following the same trend. It's taking about 3 minutes to go from solid to melted until you get to all liquid. So in this plateau, in this phase change area, you're putting heat in, but you're not seeing a temperature change. And so all of that heat has to change into something, and it transfers into potential energy, and that's what allows the molecules to spread apart. As the molecules are totally spread apart now, they have equal spacing, they're in the liquid form until you get to this plateau. Again, this has to bridge the gap between the liquid and the gas. All right, so these little flat areas, these plateaus, are just kind of like little bridges to connect basically those two states of matter. Because just like when I was boiling that solution, it didn't happen instantly. I just had a little bit of liquid in there, and it still took, you know, a couple, 3, 4, 5 minutes to boil off and change all of that liquid to a gas. So that's kind of like that bridge phase. It just kind of lets both phases, like this phase, turn into this phase, or this state turn into that state. Okay. So endothermic is the process of absorbing thermal energy. It's taking heat in. We've had endothermic and exothermic before when we were talking about chemical reactions, right? And so in a chemical reaction that's endothermic, it is taking heat from the surroundings into the reaction, right? And so, you know, that's when things would warm up because it's taking heat in. So these are the processes that go with heating curves. It's taking heat in. It sounds like endo. So the hands are absorbing that thermal energy, right? So the hands are benefiting from that heat. Hands are taking the heat in, endo in. Okay. Again, here it's back to showing energy, so thermal energy being added throughout the system. We still have temperature on our dependent variable axis over here. So we're back to looking at water because here's 0 and here's 100. So this is our bridge area, right? Our plateau, our 3 Ps with the phase changes happening and potential energy changing, right? So if you notice at these plateau areas, the temperature is constant. That means kinetic is constant. And if kinetic energy is constant, then that means that energy has to be changing into something, which is changing into potential at those phase changes. Okay? So, we know that the melting process is the energy required to change from solid to a liquid, and it's breaking some of those attractive forces. That's where the potential energy is increasing because it's having the potential to change the spacing between the molecules. And the other phase change that happens is evaporation, a liquid going to a gas. This is bridging between the liquid state and the gas state. And all the attractive forces are broken. Potential energy is going up, temperature is staying constant while that's happening, and it's not going to start going up again until all of the molecules have all the attraction broken and they are all in the gas form. Steam and sweating. There's this little novelty thing called the drinking bird. I'll have a picture of it on, I think, the next slide, maybe. Maybe not. There'll be one somewhere. Okay, so AB, if you look off to It's in the bottom right corner, of your page. And then if you turn it over, that same graph is repeated, just so that you can see those segments. All right, so we're gonna be looking at what goes on, and we're gonna be looking back at this graph. So this is the one that's in the bottom right-hand corner of your page 4, and then it's also in the top right-hand corner of your page 5. So this is the graph that we're gonna be saying A, B, B, C, C, D, looking at those different segments. So if you're wondering where those letters came from, it's from those two graphs. Okay, so, there we go. AB is the heating of a solid. You only have one phase present. It's all, in this case, usually if you're talking water, it's all ice. Right? Kinetic energy is increasing because the temperature is increasing. And you can see that on the graph because the line's going up. It's slope upwards. And then when you get to that first plateau, that BC, that flat line area, you have two phases present. You should have some solid and some liquid. The kinetic energy is remaining constant, and I know that because the temperature, it's like flatlined at 0, 0, 0, 0, if we're talking water, right? It's stuck at 0 during this melting process. Potential energy is on the increase because heat's being put in, and that heat has to go to something. If it's not going into kinetic energy, then it has to be increasing the potential energy. And then we start to rise again. At CD, it starts to move upwards, and it's the heating of a liquid. It's all liquid, so there's only one phase or state present, and the kinetic energy is increasing, and we know that because the temperature is increasing. The line is going up. And then D and E is another bridge. It's connecting the liquid to the gas states. Two phases are present, which means the potential energy is increasing, which means the kinetic has to stay constant. And the other way is you can see that it's flat. It's at 100 degrees. It's not, the temperature's not staying. It's at 100 degrees until it starts to rise again. So that whole time, kinetic energy is constant. It's kind of like hanging out just the way it is. And then as soon as it all turns to a gas, kinetic energy will start to, the molecules will start moving around again. And that last little segment is EF. It's kind of like sticking up here. And back to one phase, it's all a gas. And you can see that the temperature is going up because the line is pointing upwards. And that means kinetics going up as well. And we can tell when the kinetic remains constant because the temperature is not increasing. They do the exact same thing. Whatever one does, the other does. So if you ever get stuck, I think it's always easier to try to just find what the temperature's doing and then know that kinetic's doing the same thing. So if kinetic's going up, potential's constant. If kinetic is constant, then that means potential has to be changing. Right, so one is always going to be changing and one is always going to be constant when we're talking about those two types of energy. So plateau, phase change, and potential energy. Those three P's go together. It's weird, but it does actually help you remember it usually. Okay, let's end with this video.
In this video, we'll be looking at the sublimation of iodine.
Let me stop this first. That's weird.